Okay, so in the last video we kind of reviewed Newton's first law, and we talked about different types of forces and how to draw free body diagrams. Okay, so remember an FBD is a free body diagram, and the purpose of a free body diagram is not to show which way an object is moving necessarily, but to show which way the forces acting on an object are acting. Okay, and the size of the arrows represents the relative strength of those forces. Okay, so the longer the arrow, the stronger the force. Okay, so let's do some examples just to review. We have a free body diagram here to the right, and it says an FBD is shown for a box which is initially sliding across the floor and moving to the right. Which of the following statements must be true? Now, remember that you cannot look at an FBD and know which way the object is moving. Okay, so if you're looking at this FBD, you see there's an arrow up and an arrow down. Those are the same length, and so when we go to calculate the net force, those two forces are going to cancel out. The arrow to the right is longer than the arrow to the left. Okay, that does not mean that the object is moving to the right. Okay, all that means is if you think in terms of the net force, when we add up these two forces, let me make this a little smaller. When we add up the normal force and the weight, the force of gravity, those two are going to cancel out because when we add those together, we're basically adding two forces that are the same size in opposite directions. Okay, but F is bigger than the force of friction, and so the net force, I would say F net. Let me erase that. The net force okay, so I would say that the net force is to the right. Okay, so the free body diagram does not tell me that this object is moving to the right, it just tells me that the net force is to the right. Now the question says that the box is initially moving to the right. Okay, that statement has nothing to do with the free body diagram though. Okay, so in this situation we're told that the object is moving to the right. That means the velocity is to the right. If the net force is also to the right, that means the acceleration of the box is to the right. If the velocity and the acceleration are in the same direction, we talked about this in a past video, but if the velocity and acceleration are in the same direction, the object is going to speed up. Alright, so let's look at these answer choices. A says the box is moving at a constant velocity to the right. The only way it could be moving at a constant velocity, according to Newton's first law, is if the net force was equal to 0, which it's not. Okay. B says the box is moving to the left. There's nothing to indicate that. Now, looking at the FBD, the force to the right is longer than the force to the left. That doesn't mean necessarily that the box has to move to the right. It could be moving to the left based off of the FBD, but the problem itself tells us that it's moving to the right. Okay, so B is also out. All right, C says the box is accelerating to the left and is slowing down. Okay, and then D says the box is accelerating to the left and is speeding up. Alright, so if you look at the answer choices, none of them indicate the correct answer. Okay, what should the correct answer actually be? Well, the box is accelerating to the right, and the reason I know that is only based off of the FBD. The force to the right is longer than the force to the left. That means the net force is acting to the right. That means the acceleration is to the right. Alright, so the statement the box is accelerating to the right is only based on the free body diagram. Now, is it speeding up or slowing down? We talked about this before. If it's moving to the right and it's accelerating to the right, that means it is going to speed up. Okay, so the correct answer should actually be the box is accelerating to the right and is speeding up. Okay, so pause there if you need to look at that. Okay, so one more quick example. It says an FBD is shown for a box which is initially sliding across the floor and is initially moving to the right. Which of the following statements must be true? Okay, so see if you can answer this question. Okay, so based on the free body diagram, we have Fn, and we have F down here. Those two arrows have the same length and in opposite directions. And so this force and this force, when I go to calculate the net force, these two forces are going to cancel out. That means the net force, the only force that's left is FF, which is going to the left. That means the net force is to the left. Okay, because the net force is to the left, that means the acceleration is to the left. Now in the problem, it says the box is initially moving to the right. So what does that mean if your velocity is to the right and your acceleration is to the left? We've also talked about that in a past video. That means the box is going to accelerate to the left and is going to slow down. The answer here should be C. Okay, A is not correct because that would require a net force of 0 because of Newton's first law. B does not have to be correct. Remember, the FBD does not show you which way the object is moving, so you can't just look at the free body diagram and say, oh, there's an arrow to the left, so it must be moving to the left. That's not necessarily true. And plus, it tells you in the problem that the box is actually moving to the right. Okay, so B is also out. And D, in order for an object to speed up, the velocity and acceleration have to be in the same direction, which we don't have in this case. By the way, that means that if we change the word right to left, if the box was initially moving to the left, okay, then the answer would be D, because then it would be moving to the left, so the velocity would be to the left, plus it would be accelerating to the left, which means the velocity and acceleration would be in the same direction and it would be speeding up. Okay, so we have talked about the concept of net force before, but today we're going to go into a little bit more depth. What do we mean by net force? Okay, so when I say net force, I mean the sum of the forces acting on that object. And by sum, I mean literally you add up the forces acting on the object. Now you have to be very careful to take into account direction, because that's a crucial part of calculating net force. Now, why do we care about net force? Well, because if you go back to Newton's first law, we saw that an object at rest remains at rest and an object in motion remains in motion at constant velocity unless acting upon by a net force. Okay, that means if an object is accelerating, there must be a net force acting on that object. Okay, so let's do 3 quick examples calculating net force. So take a look at the FBD shown on the left. If I want to find the net force here, I'm adding up the forces taking into account direction. Okay, now when I say taking into account direction, number 1, if it's moving in the negative direction, you add it as a negative number. Okay. Number 2, the horizontal forces add together and the vertical forces add together. Okay, so if I look at this is negative 10, this is positive 10. Those two are going to cancel out. Plus, I have a positive 20 and a negative 10. That gives me a net force of 10 newtons up. Okay, now why did I make this a negative? Because this one is going down. Why did I make this 10 a negative? Because it's going to the left in the negative direction. Why did I say the net force is 10 newtons up? Well, because the ones to the left and to the right cancel out. I have 20 newtons up plus negative 10 newtons down. That leaves me with a positive 10 newtons, and it's positive because it's up. Okay, take a look at the middle free body diagram. Same thing. Net force is the sum of the forces. Okay, I have 2 newtons up plus negative 2 newtons down plus 4 newtons to the right. That's positive 4 because it's going to the right, plus negative 1 newtons to the left. So what is the net force? These two cancel. 4 plus negative 1 makes 3. So I have 3 newtons to the right, so my net force, F net, equals 3 newtons, and it's to the right. Okay, what about the net force for the last one? Okay, well here we just have F net equals 25 plus negative 25. It's negative because it's going to the left in the negative direction, and so that gives me a net force of 0. Okay, so net force, as long as they give you the values, is very easy to calculate. Okay, the last question here says, which of these free body diagrams might show an object moving at a constant speed in a straight line? Go back to Newton's first law. An object in motion remains in motion at constant speed along a straight line unless acted upon by a net force. Okay, so we want the FBD that shows a net force of 0, and so that would be the last answer choice. Okay, so you should now be able to calculate net force. It's very easy to calculate. And I kind of talked about why net force is important before in terms of the first law, but now let's talk about Newton's second law. Okay, so pause it here if you need to finish writing this down. Okay, let's briefly talk about Newton's second law, which is probably one of the most important equations in all of physics. Okay, this is the only quantitative law that we have. This is the only law that has any equations or calculations with it in this unit. Okay, so we only have 2 equations in this unit, Newton's second law, and we have the equation for weight. Okay, and this is by far the more important of the 2. Okay, this is one of the most important equations in physics. Here's what Newton's second law says. The net force on an object is equal to the mass of the object times the acceleration of the object. So how can we write this as an equation? Well, net force is F net is equal to the mass, so mass is m, times the acceleration of the object, and we know acceleration is a. So here we have Newton's second law, F net equals ma. Okay, keeping in mind that the units of force, net force or any force, the units of force are the newtons. Okay, the unit of mass is the kilograms, not to be confused with weight, which is measured in newtons because weight is a force. And then, of course, acceleration is meters per second squared, which we've seen before. Okay, now keep in mind, on the last slide we talked about what is meant by net force. I'm telling you net force is equal to mass times acceleration, but of course net force is also its own thing. We talked about that on the last slide. The net force is equal to the sum of the forces. Okay, and so there's 2 different ways to find net force. Either you can add up all the forces on the object, or you can multiply by the mass. You can multiply the mass and the acceleration. And Newton's second law says those 2 things are equal to each other. Okay, so keep in mind there's 2 different ways to think about net force. And so we're just going to do one quick example, and then we'll be done with this video. Okay, so examples 1 and 2. Okay, very simple examples today. Example 1. A 14 kilogram box is accelerated at 0.5 meters per second squared. What net force must have acted on the box? Okay, well, mass is in kilograms, so this is mass. Meters per second squared is acceleration. So we have F net equals ma, that's Newton's second law. Okay, the mass is 14. The acceleration is 0.5. And so that gives a net force of 7 newtons. Keep in mind, by the way, it's not force equals mass times acceleration. It's only the net force that is equal to mass times acceleration. Okay, just keep that in mind. Example 2. A net force of 200 newtons, so of course this is a given, so this is F net, acts to accelerate a box at a rate of 4 meters per second squared. Remember, nothing has units of meters per second squared except acceleration. And we're asked to calculate the mass of the box. Okay, so of course these first couple examples we're doing are very, very easy. It's meant to be very, very easy just to get you familiar with Newton's second law. Okay, I plug in the mass, which I don't know, so that's my unknown. I plug in the acceleration, which is 4 meters per second squared. I want to get m by itself. M is being multiplied by 4, so to undo that multiplication, I divide both sides by 4. And I get the mass is equal to 50 kilograms. Okay, so those are just two very, very basic examples with Newton's second law. Remember, Newton's second law is F naught equals ma. That is the only equation of all three of Newton's laws, that's the only one that has an equation with it. In the next video, we're going to go more in depth with calculations with Newton's second law. That's probably the hardest part of this unit. Okay, so just be ready for that. As always, please let me know if you have any questions, and I'll see you guys in the next video.